Okay, well, thanks and welcome everyone to our 26th ECS and Cloud Feedback Virtual Symposium. My name is Andy Dessler, and on behalf of the rest of the organizing committee, thank you for attending. I'll just go over the ground rules. So we're going to see, it says 2 AGU style talks. It's 3 AGU style talks. I obviously didn't update these slides. So there'll be 3 AGU style talks with questions after each one. And then a short general Q&A after the last talk. If you have questions or comments, type them into the chat at any time, or after each talk, raise your hand and we can, it says we'll unmute you, but I think people can unmute themselves. We'll just call on you. So raise your hands, we'll call on you, and then you can ask the questions. As a general rule, we're always looking for speakers. So if you're interested in giving a talk, send an email to anybody on the organizing committee. You can get the organizing committee contacts on our website, as well as videos of past events. There's a mailing list sign up and other information. So again, thank you for attending, and I'm looking forward to a really great event. And I will turn it over to Jonah.
Thanks, Andy. We have 3 really great speakers today. Our first speaker is Raphaela Vogel. She's a research scientist and lecturer at the Meteorological Institute at the University of Hamburg, where she studies clouds and convective processes. So, Raphaela, take it away.
Thank you very much, Jonah. And yeah, thanks for the invitation to present this work here. Do you see the right screen? Perfect. Yeah, that's work that I did in my postdoc at LMD in Paris, together also with colleagues from MPI in Hamburg. And yeah, why do we care about tracumulus clouds? So very much because their uncertain response to warming has really remained a key source of uncertainty for climate sensitivity. And 15 years after the Bonney and Dufresne paper, 2 studies split up the marine boundary layer clouds into stratocumulus and tracumulus clouds and found that the intermodal spread, but also the difference to the observations of the CMIF 5 and 6 models is really largest in the tracumulus regime, which makes up for kind of 20% of the Earth. So satellite-derived estimates from observed natural variability show that the tracumulus feedback tends to be weak. And this is in line with large eddy simulations of idealized climate change scenarios. So the question is really what is the reason for the spread and the magnitude of TCM cloud feedbacks? And first, TCM tracumulus feedbacks are governed by changes in cloud fraction near the base of the cumulus layer, with high sensitivity models showing a strong reduction of cloud-based cloud fraction. And second, these decreases in cloud-based cloud fraction were traced to changes in the strength of lower tropospheric mixing in these models. So from these high sensitivity climate models, we can formulate a hypothesis for a strong tracumulus feedback, which is that an increase in lower tropospheric mixing leads to a desiccation of the lower cloud layer and a reduction of cloudiness at the base of the cumulus layer, so near the LCL. And this mixing desiccation mechanism is illustrated here. So it contends that an enhanced lower tropospheric mixing, for example, through a stronger cloud-based mass flux, leads to a deepening of clouds. And this deepening is compensated by an enhanced downward transport of dry air and a stronger entrainment drying at cloud base, which incorporates warm and dry cloud layer air into this cloud base and subcloud layer. And when we use the mass flux as a proxy for the mixing, we can write that the mass flux is inversely proportional to the relative humidity and the cloud-based cloud fraction. And this mechanism is consistent with high sensitivity climate models. And it's also expected to strengthen with warming due to the nonlinear Clausius-Clapeyron relationship, which enhances the moisture gradient between the surface and the free troposphere. But the mechanism is also based on a number of assumptions that might not be operating in nature. So very often we write the mass flux as a product of the cloud core area fraction times the cloud core vertical velocity, and at least in the traits, the area fraction. So this mass flux is really controlled by the area fraction of active cloud cores, which make up about 50% of the total cloudiness. So from this, we would actually expect mass flux and cloud-based cloud fraction to be positively correlated. We also found substantial variability in this mesoscale vertical velocity in the trades, which kind of could introduce variability in the mass flux without directly drying the cloud-based layer and reducing cloud-based cloud fraction. And this is not really accounted for in this mixing desiccation framework. The problem is that this mechanism was never tested with observations, partly because we never really had the observations of mixing and cloud-based cloud fraction at the relevant scale of GCM parameterizations. And as many of you might know, that was the motivation for the Eureka field campaign. And during Eureka, we used a novel sampling strategy with 2 aircraft. One aircraft flew at cloud base and measured the cloud-based cloud fraction with horizontal LiDAR and radar, but also with in situ sensors on board of the aircraft. And the second aircraft flew at 9 kilometer height and released more than 800 drop zones. And from these drop zones, I computed all the terms in the subcloud layer mass budget, which is a budget for kind of the subcloud layer height h. And when we kind of look at the equilibrium mass flux, then we can, by measuring or by observing from the drop zones the entrainment rate and the vertical velocity, we can infer the mass flux as a residual, as is noted here. So in the rest of the talk, I will first show you how we measured these variables. Then I will use the measurements to test the idea of the mechanism, and then eventually show you some results when how consistent the observations are with climate models. So to appreciate the beauty of these trade cumulus clouds, I will show you a small time lapse for kind of half of a circle that the aircraft was flying. You see that we had pronounced shear, but you also see that the clouds really pump up moisture. Then when some clouds kind of overshoot the inversion, they really quickly evaporate, as you might have seen there. So parts of the domain that we sampled had more of these stratiform cloud layers. Other parts had very, very shallow clouds. Sometimes there was also a lot of clear sky. So it's kind of a lot of mesoscale heterogeneity. And on this day, there was also a lot of dust, as you can see here in the back. Some facts about Eureka. So the campaign took place in January, February 2020, right before the pandemic. We had 4 aircraft, 4 ships, the Barbados Cloud Observatory, drones, so a huge number of platforms. And initially the motivation was to collect the measurements to test this mixing desiccation mechanism, but then in the run-up to the campaign, there were also a lot of additional science facets kind of added to the campaign. And Barbados was chosen as a location because clouds at Barbados were shown to be representative for trade cumulus clouds across the entire trades, which kind of allows us to generalize. And here I want to kind of make some publicity also for the data. We really made a big effort to make all the data available. There are a lot of data papers that explain the way we collected the data, but mostly PhD student at MPI, they also created a very nice how to Eureka book with code examples, and that really helps you get started, because I think you might have also questions that you want to answer with or analyze with our data. So then I want to show you the measurements that I kind of derived from these drop zones. So here is kind of a time series across the campaign. The solid or the full circles show mass flux estimates aggregated across 3 circles. So it's a 3 hourly 200 kilometer time scale and 200 kilometer scale. And you see that kind of towards the end of the campaign, the mass flux increased, and that was due to a strengthening of winds and strengthening of entrainment. So I don't really show you any details on how I got this mass flux, but you can ask or you can find the details in the paper. But when we look at the contributions of the different terms to the mass flux, we find that on average, the mass flux magnitude is really controlled by the entrainment rate, because the vertical velocity is on average nearly 0. But when we look at shorter time scales, and this is kind of represented here also by the standard deviation, so the vertical bar, we find that actually both entrainment rate and vertical velocity contribute almost equally to variability in the mass flux. So that's the data along the circles from the hollow drop zones. When we add the cloud fraction data from ATR that flew rectangles inside this circle, we find that the cloud-based cloud fraction is on average very small, so 6%, which means that 94% of the time we were flying in clear sky. But there is quite some variability, which is much larger than, for example, the variability that you get on timescales longer than a day. We also measured the relative humidity on both aircraft, so we can also compare whether the aircraft really sampled similar conditions. And we found that for three cases, kind of the two aircraft didn't really sample similar conditions, so we neglect these instances when we look at the relationships afterwards. And just as a note, so I made a lot of tests with the way I estimate the mass flux, but also we compared to different cloud fraction products, and we find that really the data is robust to these changes and also the relationships that I will show now. So with this data, we can now test the idea. And here I show you a scatter plot of all three circle sets. And the size of the markers shows the cloud fraction. But from this, we already see that the mass flux and the relative humidity seem to be uncorrelated. So they're nearly uncorrelated, and kind of the dots kind of randomly spread in this phase space. And this is because the mesoscale vertical velocity and the entrainment rate, they contribute almost equally to variability in the mass flux, but they have opposing relations to the relative humidity. So more entrainment, as expected, leads to a warming and drying and the reduction of relative humidity, but more vertical velocity. So if we have convergence, we get actually a moistening of the cloud-based layer, and conversely for divergence. And that wasn't really expected. I mean, it's also kind of in contrast to LES results. And our former PhD student, Guy George, he has a very nice paper that is going to be published in Nature Geoscience, I think in the next weeks, that looks more into these shallow mesoscale overturning circulations and their effect on the moisture variance. So from this, we find that the mass flux and the relative humidity, they seem to be uncorrelated. So we can use them in the regression to kind of see how much of the variability in the cloud-based cloud fraction together they explain. And they explain more than 70% of the variability in the cloud-based cloud fraction. But then when we look at the individual contribution, it's really the mass flux that explains most of the variability in the cloud-based cloud fraction. And they have a strong positive correlation. So more mixing actually leads to more cloudiness, which is really opposite of what the mixing desiccation mechanism contends. So the data, or Eureka, was conceived to test this idea. And when we look at the data, we find that the data refutes this mechanism. Just very quickly for the climate model. So how consistent are the current climate models with our observations? We find that the magnitude, the variability, but also the coupling of mass flux, cloudiness, and relative humidity in CF mid models, so in models that provide CF sites, single grid point output. So these terms really differ among individual models, but also between the models and the observations. The models that tend to have the largest positive feedback tend to represent some of this mixing desiccation behavior, and they also particularly exaggerate variability of cloud-based cloud fraction and the coupling of cloudiness to relative humidity instead of the mass flux. And interestingly, when we analyze how models represent the observed daily transition from kind of shallower daytime tracumulus clouds to deeper nighttime tracumulus clouds, we find that a very consistent behavior with the analysis of the Eureka data. So models that reproduce this observed deepening transition, they tend to be more realistic, and they tend to predict weaker tracumulus feedbacks. So to conclude, Eureka was conceived to test the mixing desiccation mechanism. The data refutes the mechanism, and instead it emphasizes convective and mesoscale motions as dominant controls of cloudiness. And with this, we also refute an important mechanism for a strongly positive tracumulus feedback, and thus a critical line of evidence for a strong climate sensitivity. The data also renders climate models with strong positive feedbacks unrealistic, and it supports and explains at the process scale a weak trade cumulus feedback. And you find more data, more details in the paper. Thank you very much for your attention.
Awesome, thanks. That was a really great talk. And thanks for sharing the videos. It's really fun. I had a quick clarification question, which you might have said, but how are you guys measuring cloud cover?
So we measure it with horizontal LiDAR and radar. So it's kind of a synergy of a LiDAR and radar product, because the LiDAR is really sensitive to very small clouds, and the radar also can kind of penetrate the deeper clouds. So it's kind of a remote sensing product from this aircraft that flew at cloud base. Because if you want to measure cloud-based cloud fraction from the other aircraft, that's not really possible, because you don't really get to the cloud base. But then we also measure it from fast humidity fluctuations. So whenever fast humidity, or the relative humidity is larger than 98%, we can also consider that as a cloud. And these two estimates are quite consistent in their variability and the magnitude.
Great, thanks. Are there any other questions for Raphaela? Okay, I'm not seeing anything, but a lot of times people write questions in the chat later, Raphaela. So if you could just monitor that. Sure.
Yeah, great. Thanks a lot. So I'll unshare.
Thank you so much, Raphael. That was a great talk. Our next speaker is Daniel Koll. Daniel is an assistant professor at Peking University, where he studies the theory of planetary atmospheres, both the Earth's and those of exoplanets and other exotic planets and such things. Daniel, take it away.
Okay, thank you, Jonah, and thank you to all the ECS organizers. Let me first check. Can everybody see this okay?
Yeah, that looks good.
Wait, I'm trying to find the annotation dot. God, okay. Spotlight. Okay. I'm not going to do it this time. So if there's something that I want to point out, I'm just going to point it out verbally. So, hey, everyone. Yeah, so my name's Daniel. What I wanted to talk about today is the clearsky longwave feedback. And some of you might be a bit surprised what's still left to talk about, because after all, we've already had pretty great talks in this ECS symposium series on the topic. Just recently, I think in the last year, Bjorn was talking about it, Nader. Yeah, so I'll give you a particular slant about it. And what I'm really talking about today is this paper at the bottom, which was done with my colleagues Nader, Javanji, and Nick Lutzko. And that's out in Journal of Atmospheric Sciences now. But let's take a step back. So this is the ECS symposium, right? So how does what I want to talk about fit in with ECS? So the ECS, let's take it as defined as the forcing due to CO2 divided by the climate feedback, gives us the equilibrium climate sensitivity. Now, how do we understand ECS? And lots of great work out there. I would say it's sort of like probably a fair thing to say that many of us would agree there's roughly 3 lines of evidence for constraining ECS: the historical record, the paleoclimate record, and physical reasoning. And what I want to talk about today, all of this talk is really about physical reasoning. And why is that? And it's, I think there's some issue, well, there's 2 interesting issues, which is like to use the paleoclimate record to talk about ECS tends to be a bit difficult because we can't just take paleo data directly if F or lambda have state dependence, right? Like if F or lambda in turn depend on the climate that you're in, then it's very difficult to take, say, a past hot climate to say something about ECS now. Similarly, it's kind of difficult to take the historical record to say something about ECS if there's regional dependent, and that there's been a lot of recent work talking about the pattern effect, which is basically making exactly that point. So what I was interested, or what we were interested in this work, was actually sort of, can we understand a little bit more, build towards a better understanding of state dependence and regional dependence. And of course, the main line of physical reasoning that we have tend to be global climate models, complex numerical models. They're very important, but if you have a GCM, it's not very obvious to understand something about state and regional dependence. So the goal for today, we're going to do it a bit different. And what we're going to talk about today is a simplified version of the feedback, namely only the long wave clear sky feedback, which I'm going to call lambda_LWCLR. And why do we do that? Well, because the clear sky long wave feedback is thought to be much bigger than any of the other feedbacks that we have. So surface albedo, clouds, etc. The net value of that is actually dominated by the long wave clear sky feedback. So it's a very natural starting point if we want to also start thinking about things like state dependence or regional dependence, because even a small change due to state dependence in the long wave clear sky feedback could have a large influence on the overall state dependence of ECS. All right, okay. How are we going to do that? The way we tried to do that in our recent work was to think about these things by turning to pen and paper. So we want to have some kind of way to, say, derive analytical expressions for the feedback as a function of various climate variables. So say the global mean temperature, relative humidity, etc. And just there's already been a lot of great work done recently on actually developing analytical models for the forcing F CO2. So I'm not going to talk about that today. You can check out all these great papers by many different authors like Nader, Jake, David Roms, etc. So what I'm going to talk about today is trying to do work with pen and paper to understand the long wave clear sky feedback. And that in turn is going to hopefully give us some idea ultimately about where about ECS. That would be the large goal, right? But the talk today really is about this long wave clear sky feedback. Okay. With that said, is there anything interesting to say? Because every climate scientist sort of like tend to learn that, well, the long wave clear sky feedback, we know it quite well, models agree on it, and we also have an idea of how to explain it, right? Because we know we can be split into Planck, collapse rate, and water vapor feedbacks. Now, my argument would be that actually this decomposition, which I'll call the traditional decomposition, has some issues. In particular, if you want to talk about, say, state dependence of the long wave clear sky feedback, it's really not obvious. Why? Well, in a warmer climate, we all know that Planck, lapse rate, and water vapor feedbacks all have to get bigger, right? But just because they're bigger, but they're opposing, it's very hard to say what their net effect is. So what we did in this paper was something different, and we viewed things in terms of spectral space. So what that means is we take the long wave clear sky feedback and we split it up into the different parts of the spectrum, which are going to be the surface feedback. It's also called the surface kernel for people who use radiative kernels. Then the feedback coming from the CO2 bands, so the parts of the spectrum that are dominated by CO2, the water vapor bands, which is parts of the spectrum that are dominated by water vapor, and then another feedback coming from the water vapor continuum. You could add lots of other greenhouse gases in here because each greenhouse gas would occupy another chunk in spectral space. But what we're doing is we're imagining an idealized atmosphere where there's only CO2 and H2O as the only greenhouse gases, right? And so our goal is to understand that. The good news is that it works. I'm not going to walk you through the math because the math gets a bit long and too long for this kind of talk. But the brief takeaway message is, if you work in spectral space, you can develop analytical expressions for all of these spectral feedbacks. So what we did in the paper, which you can check out after this talk if you're really interested, is we imagine a vertical 1D column of atmosphere isolated from everything else. The state of the column is given by the surface temperature, the lapse rate, the change in lapse rate under warming, stratospheric temperature, etc. And we ask, how does the OLR of this column change under 1 degree of surface warming or something? And then we look at these in different chunks of the spectrum. And by doing that, we were able to develop analytical expressions for all these spectral feedbacks, which gives us the net long-wave clear sky feedback. That's great. So let's again skip the math. I'm just going to talk about what we've learned from that exercise. One note before we go to the results is that because we're thinking about an isolated 1D atmospheric column, the state dependence of the feedback in that column is actually the same as the regional variation, meaning that if I take this column and I make the surface temperature cold versus hot, this could as well represent a difference in state dependence between a cold climate versus a hot climate, versus looking at the local feedback on the local long wave clear sky feedback in Earth's poles versus Earth's tropics. Okay, so here's the result. So what this plot shows is a calculation that two calculations I did. One was with a pretty sophisticated 1-by-line radiative code. So we take a vertical 1D column, and then we heat it up through a bunch of different surface temperatures, and we compute feedbacks in this different part of spectral space. And that's shown by the symbols. Like the black is the net feedback, and then the green, blue, and red dots are the decompositions into the different parts of the spectrum. The important part is that here, for example, you can see the black feedback starts out high at low temperatures, and then it goes down, down, down at around 300K. It gets very small. Why? Because the surface, when the feedback from the surface gets cut off, because the atmosphere becomes more and more filled with water vapor. So the surface cannot radiate to space anymore. Then it becomes very small at high temperatures. There are two other feedbacks though. One is from water vapor, which as you warm the surface, actually the water vapor bands still give off radiation to space a little bit more. And then there's the red dots give the continuum feedback, which destabilizes it because it has the opposite sign. Now here's a calculation where we've added CO2. And you can see that now we get these orange dots added. So now we get an additional feedback because the CO2 bands actually also give off more radiation to space as you warm the surface. And that gives another stabilizing feedback. And you can see here that the dots are complicated numerical calculations. The lines are our simplified analytical expressions. So you can see that whatever things we wrote down, where the math again is a bit messy, whatever math we wrote down, it seems to capture what's going on in the dots quite well. So we think we can understand things in terms analytically. One punchline here about the state dependence is that the surface feedback always tends to decrease with warming because the atmosphere becomes more and more filled with water vapor, which cuts off the emission from the surface. On the other hand, surface feedbacks coming from H2O and CO2 increase with warming because the lapse on a moist adiabat, the upper atmosphere warms more and more and more as surface warms. Okay, and you can use this to explain the ECS maximum that was found in other papers. For example, Seeley and Giovanni found that there's an ECS maximum in many models at 310. Why is that? Well, it's because the surface feedback goes down and the atmospheric feedbacks go up. And so in between you get a well. And you can use our model to explain all of that. So let's say check, this is a check. We can really say something interesting about the state dependence of the long wave clear sky feedback. What about regional dependence? I'm going to go through this, but what we did there is to check whether our math was really making sense. We did one, a radiative kernel calculation, and one, we did just calculations using our analytic expressions. So the radiative kernel calculations, you use a radiative kernel and GCM data from a forced response and a pre-industrial response to compute maps of the long wave clear sky feedback. And then you just take the state of the GCM, mostly the pre-industrial state, and you can also compute using our analytical expressions what the map of the feedback would be. The left map is this complicated calculation with GCM kernels. The right map is just using our analytical expressions. The nice thing is they match really well. So what we can use, what we've learned about our analytic feedbacks, we can actually use to say something now also about regional expressions. let's go. I'm going to skip through parts of it. One interesting I'll see. So for example, here on the map of the long wave clear sky pattern, why is this map, at least in this GCM, why it is, right? It's, for example, here, the net feedback is small in the ITCZ, large in the subtropical desert regions, and very large in these hotspots on the subtropical ocean basins. And we can use that to explain it. It turns out that for the ITCZ and desert regions, it's because the surface feedback varies a lot with column relative humidity. So that gives you these hotspots shown in blue here. And for these other spots that are circled here in yellow, this turns out to be mostly dominated by the lapse rate changes, which in turn dominate the atmosphere's feedback. And we have analytic expressions for that, so we can play around with them. Okay, so let's come to the conclusions. What do we learn from that? I mean, A, we take the clear sky long wave feedback and we decompose it spectrally. That's really the new thing. Why do we do that? It allows us to not just say something about what is the value of that feedback today, but we can also explain its state dependence and its spatial pattern. So for the spatial pattern, it turns out it's mostly about the surface, but inside the tropics, there are important secondary feedbacks coming from the CO2 and H2O bands. If you put this together, now if you say we have sort of like a way of using pen and paper to estimate just the long wave clear sky feedback, since we also have a way to talk about CO2 forcing, that was some work that were done by people including Nader and Jake Seeley and other people, we can actually put these two things together to start to talk that we can say we have something starting to be a first simple spectral picture of ECS, as well as ways of talking about the state dependence and regional dependence of all the things in that. Okay, this is still idealized. If you have questions about what's not included in here, you can ask me afterwards. Thank you.
Thanks, Daniel. Great talk. Are there any questions for Daniel? I'm seeing a lot of claps. Oh, Priyam has a question. Maybe Priyam, do you want to unmute yourself and ask it directly?
Yeah, thanks, Daniel. Really great talk. I was just wondering, is there any thoughts you have that you could include clouds into this analytical framework? I'm not talking about the cloud feedback, like clouds changing in response to warming, but just the presence of clouds, like an all sky feedback.
Yes. The simple answer would be, well, at least the long wave part of the clouds actually gets very easy. And I would encourage you, a cloud, if it behaves like a black body, it just means that you're moving the surface towards a colder surface temperature. So let's go, I'm flipping back to these plots. Imagine you are in a climate where the surface is at a toasty 300 degrees K. Then the surface feedback, what we would expect for that is this green dot here. But now imagine that this surface of 300K is covered by a cloud, but the cloud itself is only sitting at 260. Barring cloud feedbacks, like what you said, then the overall feedback that's coming out of this column would actually be higher, because you're basically moving the black body emission coming out of that column instead of the surface, which is deep down and buried by a lot of water vapor, higher up into where it's above a lot of the water vapor. And so therefore that cloud can actually radiate more efficiently than the surface because it doesn't have that much water vapor above it. There was a nice paper by Bjorn Stevens and Lukas Kluft talking about exactly this kinds of stuff with clouds that I encourage you to check out.
Thanks.
There's a question from Kyle.
Yeah, thanks for the great talk. I had a question about what you meant by the CO2 feedback here. Is that just a changing CO2 forcing normalized by the temperature change or something something more subtle going on?
No, this is, yeah, so this is where short time, this is the unintuitive. Climate scientists are all used to thinking of CO2 as a forcing because it decreases the radiation to space. But it turns out that if you have CO2 inside the atmosphere compared to an atmosphere without CO2, if you warm that atmosphere, the presence of CO2 allows you to radiate off more energy to space than you could otherwise. What I'm showing here is actually a spectral plot. So a wave number on the x-axis, and on the y-axis we have oops, the wave number, actually the labels are wrong on the x-axis. I pasted the wrong ones. But on the y-axis, you have the emission temperature, which is sort of like the emission where radiation goes to space. The bump in the middle on this plot, unfortunately falsely labeled at 650, is that little spike there. Sorry, I can only talk about it, is the CO2 band, right? And now what we can see is here, the region marked in orange. And what we can see in this column, like the solid lines are all 1D line by line columns. If we warm the surface, you can see that this spike gets, wait, let's see. Wait, I'm messing, did I mess myself up? Let's just say this. In the CO2 band, if you warm this column, and actually, I think I might have grabbed the wrong plot for this, but if I had the right plot, you would see that the emission actually grows as the atmosphere gets hotter. CO2 gives off more energy to space. Sorry, did I? I'm not sure if that was clear. Otherwise, you can maybe put it in the chat, and I'll try to respond to it.
Yeah, I think that makes sense. Okay, got it. Thank you.
Okay, Jonah put another paper in the chat. Are there any other questions for Daniel? If not, we'll move on. And yeah, Daniel, if you could just keep an eye on the chat. A lot of times questions come up there.
Thanks, Daniel. That's a great talk. Our final speaker for today is Pedro DiNezio. Pedro is an associate professor at the University of Colorado Boulder, where they study the climate dynamics of the tropical oceans. Pedro, whenever you're ready.
Awesome. Thanks for letting me present this research here. It's very new. It's the first time I present it, probably in its almost full form. A lot of credit here goes to my collaborators, especially Ping Chang, that run this relatively small ensemble of high resolution simulations with the CSM, which costed them a lot of effort and time and hassle and even geopolitical tensions. So I could not have done this research with these simulations, and a lot of people that helped me think about this problem. So we started to think that standard resolution CMIP models might be producing an erroneous response in the tropical Pacific or the Pacific in response to external forcings. And this is evident in the last 40 years when you all know this, the Pacific has been cooling and the temperature gradient across the equator has been strengthening and the Southern Ocean has been cooling along with it. And if you take a multi-model ensemble mean trend for this interval, in this paper by Rob Wills, starts in 1979. The trend is almost 40 years. You can see that the ensemble mean of all these models cannot reproduce what we see in nature. I studied this problem when I was a PhD student, and back then, we thought that it was internal variability and that eventually the trend will reverse, but it has been going for a long time now. And it's every year that passes and the tropical Pacific continues to be on that state, we're starting to ponder alternative explanations. In Rob's paper, he computed the temperature gradient west minus east across the equator in all these models that had relatively large ensembles. So each circle here is one single realization of the models, and you see that in the observations, the Western Pacific warms more. That's the positive value of this gradient in the solid black line across this graph. And you see that very few realizations of these models can simulate it. So still could be that nature is a fluke, where just natural variability is producing this trend. But as I said before, every year we start to consider alternative explanations. So one alternative explanation is that the models are wrong. So I wanted to explore, well, what about the models is wrong? So what's nice about these simulations, these results from these simulations that I'm going to present today, is that we have these, I'm going to do a comparison of the exact same simulations, historical plus RCP 8.5 performed with the high resolution version of CSM and the standard resolution, which is what we call the large ensemble. So the standard resolution, everyone is familiar, is typical CMIP resolution, 1 degree atmosphere, 1 degree ocean in the horizontal resolution for both for the ocean and the atmosphere. The high resolution simulations that I'll be presenting are 1/4 of a degree in the atmosphere and 1/10 of a degree in the ocean. So it's close to a degree resolving in the ocean. Everything else in these two models is the exact same. Vertical resolution is the same. The physics in CAM5, this is CAM5, it's the same. So the forcings are the same. And actually the climate sensitivity of these two configurations is about the same. So as I said, the same forcing, one ensemble has 40 members, the other ensemble is naturally smaller because it's really expensive to run these simulations. So I'm using 3 runs that are part of the IHES project, and 1 run that was contributed by the project to high-res MIP. So 3 runs initialized in 1920, the other run initialized in 1950. And I'm going to be focusing on 2 analysis intervals, starting in 2023, this year, into the future, just to see if there's differences in the force response. And for over this long period with strong forcing, we don't have to worry about internal variability. And this is how I started studying this problem, because we know that natural variability is very important, a very important driver of trends over these 40-year periods, these multi-decadal periods. And then I'm going to focus zeroing into the 1980 to 22 period when the observations show all these intriguing trends in the Pacific. So focusing on the future, from now to 2100, you can see, I'm going to be calling them CSM1 HR and low R. I'm showing ensemble means of the trends, linear trends over these periods. And you can see that the trends are not that different, but if you focus on the Southern Ocean, there's a bit more cooling. It's actually absolute cooling in the high resolution version of the model. On purpose, I pick a color scale that has blue colors to show absolute cooling. So the model is doing something different when you have ocean eddies and high resolution in the atmosphere. And if you look at the individual 4 members, again, I'm working with very few members. So we have to be careful that these differences are not the product of internal variability. You can see that all these realizations show that absolute cooling in the Southern Ocean. I could have used a different color scale to emphasize this more, but you get it. It's actually a few degrees of cooling relative to the low resolution large ensemble. So now we can focus on the last 40 years, 1980 to 2022. We have the observations, which we're all very familiar with from ERSST5, the 4-member mean from the high resolution model, and the 40-member mean from the low resolution, from the lens. And you can see that the differences are even more pronounced, with cooling in the subtropics, a different temperature gradient across the equator, and cooling in the Southern Ocean. So what's that funky stippling that I chose? Well, I spent months doing the statistics of the differences between these 2 ensembles. So after bootstrapping the large ensemble into 4-member ensembles and comparing them, I found that wherever there's an open circle, the trend in the 4-member ensemble is totally outside the distribution of any 4-member ensemble from the lens. So subsampling the lens with its 40 members, you can create 90,000 different 4-member ensembles. There's not a 4-member ensemble in the lens that looks like the high resolution 4-member ensemble in those places where I have the open circles. And then the little dots, it's where it's outside the 95 percentile range. So clearly, the high resolution model is doing something different. And you can look at the individual members. Those are the 4 members with the trends over this interval. And you can see that there's differences that arise from internal variability, but they all show less warming and in some of them cooling in the subtropical South Pacific and in the Southern Ocean. If you look at the lens, you'll find realizations that will have warming in the Southern Ocean and warming in the subtropical. So we have 4 members that are entirely different from any members in the lens. But when we look at the distributions of some key indices, so if we look at the equatorial SST gradient, so east minus west, I use a different definition that Rob's, just a change in sign. So the observations are negative here. Gray is the distribution from the lens, from the 40 members, and blue is these 4 members. And you can see that for the equatorial gradient, there's still an influence of internal variability, but all these members are towards the observations, towards strengthening temperature gradient. In the southeastern tropical Pacific, the center distribution, you see that the members are even more biased towards the observations relative to the distribution of the 40 members from the lens in gray. And if we go to the Southern Ocean, we also see that these 4 members are, although some individual members in the lens look like them, together averaged, they're completely different from what the lens can simulate. We can see the same thing for sea level pressure, which can tell us what the Walker circulation and what the atmospheric circulation does. So the same type of plots, observations, the high resolution simulation, and the low resolution ensemble. So these are the ensemble means. And you can start to see how the 4-member mean from the high resolution ensemble, it's a lot closer to the observations. I'm going to walk you quickly. So the individual members, the one thing to identify here, which I think is interesting, is that this one member, member 1, can reproduce what we see in the tropics, like a stronger Walker circulation with high pressure in the subtropics without a trend in the sum. So this member doesn't have a trend in the sum, which is one of the explanations that has been proposed for the Southern Ocean cooling and for the trends in the tropics. But you can see this clear teleconnection pattern emanating from the equator, which is present in all these 3 members, a typical stationary wave triggered by changes in rainfall in the equator, in all 3 members. And I can do the same thing, but I want to focus on the Southern Oscillation, the off-equatorial Southern Oscillation, so the traditional Walker definition, sort of Darwin minus Tahiti. And you can see that these 4 members are very outside the distribution of the lens and a lot closer to the observations. So what is the mechanism? I want to just tell you what I think it's going on in this model that has higher resolution. Luckily, I was able to find a 4-member ensemble. This was run by Jerry Mills' group at NCAR. It's the same, almost the same code that used for the completely high resolution ensemble. But here, the atmosphere is high resolution and the ocean is low res. So we can tease out a bit of what's going on. And the first thing you see is that there's no Southern Ocean cooling when we don't have ocean eddies. So first thing here, no ocean cooling. The stippling is the same thing. So you can see that this 4-member ensemble, it's a bit more noisy and it doesn't produce such strong cooling in the subtropics, but it has some features that are different from the totally low res ensemble. So both ocean and atmosphere, increased ocean and atmosphere resolution are important for getting closer to the observed trends. Something that I think it's key here is the simulation of the tropical climatology in the mean. So what I'm showing here is during MAM, when the double ITCC bias is most pronounced in standard resolution models, is where we see this cooling starting to propagate, or this subtropical cooling starting to propagate into the equator. So you can see the full high-res model without a double ITCC bias. I mean, there's still deficiencies in the simulation of the tropical climatology, but it's not as bad as in the the standard resolution models with a totally unrealistic double ITCC, which prevents the off-equatorial SST anomalies from propagating into the equator. Because essentially the southeast trades don't blow all the way. And this is the climatology. I'm not talking about the trends. So the southeast trades in these models, the standard models, don't blow all the way into the equator during this season. And this off-equatorial or this subtropical cooling cannot penetrate into the equator. So this is part of the answer. And I'm going to propose a mechanism which is not fully demonstrated on why a high resolution model can simulate these patterns that are structurally different from what standard resolution models do. When the climate warms, there's a warming minimum in the subtropics because it's where evaporation is stronger. It corresponds with the strongest wind speeds. That warming minimum can propagate into the equator because in these models, we don't have this double ITC bias, particularly in MAM. And it produces increased rainfall. I didn't show you the changes in rainfall, but the patterns are entirely different between the high-res and the low-res models. The high-res models simulate a lot more rainfall over the SPCC in the Pacific. That increased rainfall is what drives that stationary wave that was very prominent in the SLP changes. And these SLP changes strengthen the southern hemisphere westerlies, but locally. It's not a SAM response. It's just the local response in this region of the strongest Southern Ocean cooling. Because we have eddies in the ocean, we have a stronger response or a more realistic response in the overturning, meridional overturning circulation in the ocean, which will produce more upwelling. There's a different response with the eddy saturation and compensation in the Southern Ocean. And that Southern Ocean cooling then makes it through atmospheric advection into the subtropics. It strengthens the subtropical cooling, which closes the loop and producing more increased rainfall, and then the stationary wave that strengthens the westerlies. So hopefully you think this mechanism is viable. Increased atmospheric and ocean resolution produce externally forced responses in much better agreement with observed trends. Internal variability, it still plays a role, but a lot less than in standard resolution CMIP models. The effect of atmospheric resolution, I think it's mainly improving the rainfall climatology, allowing the subtropics to influence the equator. And the ocean resolution improves the oceanic response to the changes in the westerly winds, because we have eddies, and eddy compensation and eddy saturation is a lot more realistic. Even though CSM has a parameterization that is state dependent, still the response is different to changes in the winds. And there's some results about that in a paper that Steve Yeager just, I think, submitted, showing that having eddies improves the response in that sector of the South Pacific to changes in the winds. So the trends in the SAM might not be as important as previously thought, and it's more these two-way feedbacks between the subtropics, the equator, and the Southern Ocean. And therefore, the ongoing trends in Pacific climate may have a much larger anthropogenic influence that inferred from standard resolution models. I'm going to stop there and take any questions.
Thanks. This is a really intriguing talk. Are there any questions for Pedro? One question I had is I think you mentioned that you had looked into this a little bit in the high-res MIP models. Yeah, I was wondering if you could talk about that a little bit.
That's a good question. No, I'm using only the CSM contribution to high-res MIP to enlarge my ensemble, because ensemble size is critical to do this. So going from 3 members to 4 members change some of the bootstrapping that I did. Still, the difference is so large that with 3 members, I could have proved this. But I mean, there's an extra member being run now on Frontera. So soon we probably have 5 members and maybe 6 by the end of the year. High-res MIP has a more of a mix of increased resolution in the atmosphere and in the ocean. And the reason why I did it, I mean, if you look into high-res MIP, you'll see a difference also, but it's not as clear. And this analysis, because I'm using the exact same model, everything is the exact same, but the horizontal resolution. But you see some, not as pronounced.
Okay, great. Raphaela has a question. I think Andy might as well, but Raphaela, go ahead.
Thanks a lot. So if I understood your mechanism correctly, then it depends very much on how much moisture is exported from the trades.
Yeah, I mean, if you're familiar with the literature on these mechanisms, this idea was proposed in a paper by Dong and collaborators. Kyle was a co-author on that paper, that of this two-way feedback.
Okay,
In their mechanism, they trigger this response by cooling of the Southern Ocean. What I'm changing here is that the response is triggered by that minimum in warming that then becomes cooling when the feedback is amplified. So you produce that minimum in warming in the subtropics just because the wind speeds are stronger. So if you apply a uniform radiative forcing, if you have higher wind speeds, you need a smaller temperature change to compensate that uniform radiative forcing done on the equator. So that's pretty well known that the subtropics will warm less in response to greenhouse gas forcing because of the higher wind speeds.
Yeah, I just wondered then, but maybe I should read this paper. Because I mean, it will depend how much moisture can be exported from the subtropics, will also depend on how much rain falls in the subtropics, because you might just rain more of the moisture out right there. So it depends on how well your warm rain is simulated. And I wonder whether you have whether you know how, I mean, I don't know, would you have parameterized convection, I guess?
Yeah, totally.
Okay. I just think that could be an important component as well then, but.
Yeah, I haven't thought about that. I think it's probably a bit more simple. It's probably just having a better resolution of the Andes improves your simulation of the ITCZ, and we're still in a parameterized regime for the atmosphere at this horizontal resolution.
Okay, thanks.
Okay, Andy.
Yeah, just a quick question. I think you probably answered this question already, but I didn't. I think I may have missed it. What does the long-term forced response like 2100 look like in the high res versus the low res? You know, is this? I'm sure you showed a picture of it, and I just didn't think of the question.
Yeah, no problem. I showed it in the beginning.
At the beginning, yeah, I realized I missed. By the time I thought of the question, I missed it. So.
Here you have it. It's actually not that different. So this response might be, you're right, what I show for the last 40 years, it might be more pronounced. And I don't know the answer why, right? For the last 40 years, you have this bigger La Nina-like response. And as you go into the future, the conventional response is a bit more evident. Although I think there's structural differences in these two patterns. Right, you have
but the model still looks like you know, sort of the canonical wisdom that the response will look more like an El Nino still is true.
And again, I don't know the answer why at some point this pattern wins over the subtropically driven cooling pattern. It's a good question.
Very interesting. Thanks.
Yeah.
Okay, we're starting to drop off, but one last question from Nader.
Yeah, thanks, Pedro, for the very intriguing talk. By the way, on that last point to your question, Andy, there's some interesting papers by Uli Heed and Alexei Fedorov talking about sort of the transient nature of this force response with the, suppressed warming in the East Pacific, followed by the more El Nino-like pattern, which you might check out. Pedro, I'm wondering about these, the different resolution dependence in the atmosphere and the ocean that you talk about, just sort of how robust or how well understood they are. So in the atmosphere, it sounds like you're saying that at slightly higher resolution, but still not convection permitting, you get a reduction in the double ITCZ bias, and therefore your precipitation climatology looks better. Is that a robust result, or just something that you find here in these IHES simulations?
That's a good question. This was found in the previous high resolution simulation with CCSM4, the previous version of this model. So I think it's improvement that comes from, I think it comes from topography. And along the Andes or in Central America, I mean, there's results showing that the interaction between the Caribbean and the Northeast tropical Pacific matters for simulating the position of the ITCC. I think, there's high-res MIP now, so I could probably look into that more.
Yeah, maybe people have already looked into that, or if not, it would be interesting to cross models.
Again, I don't know exactly what makes such a clear improvement in the climatology.
Yeah. And then similarly for the ocean, so it sounds like you're saying that increased ocean resolution and the eddying capability of the models gives rise to this, enhanced cooling in the Southern Ocean. Is that something we sort of understand mechanistically, or we see in other models? Do you know?
That's actually very intriguing to see, because there's this idea that as the winds strengthen, eddies compensate the large-scale response in the ocean, and then the ocean at some point will not do compensation, and it could start upwelling cold water. And there's a lot of research on that, and CSM, the coarse CSM, so the coarse CSM has a parametrization based on the best knowledge of all that response to simulate how eddies would respond to changing winds. Yet, when you resolve the eddies, you get this stronger cooling. And Steve found the same thing in decadal prediction. So there's a companion decadal prediction large ensemble with these high-res simulations, and they found the same, and they associate, they show clearly that is the overturning circulation in the Southern Ocean, the way it responds to changes in the winds is entirely different when you resolve the eddies than when you parameterize them.
Cool. Thanks. Very nice application of the IHEP simulations.
Thank you.
Yeah.
Okay, I really need to get going, but there's two kind of related questions in the chat, which maybe we can answer super quickly. So Stephen Pochedley asks, is the global average warming approximately the same in 2100 in the two sets of simulations? And then Nick Lewis asks, at what point do the warming patterns converge, since the ECS of the two sets of models are similar, of the high and the low resolution models are similar?
Yeah, the warming is about the same. The climate sensitivity it's really close between these two configurations of the
Yet
models.
the patterns are different?
Yet these patterns are different during this interval. Eventually they converge. I don't know exactly when, but these data are sort of public, so you're welcome to look into that problem.
Yeah, okay. Well, I need to run now, but thanks everyone for coming. Thanks to the speakers for a really great set of talks. And see you guys all next month.